Beam-powered propulsion, also known as directed energy propulsion, is a class of aircraft or spacecraft propulsion that uses energy beamed to the spacecraft from a remote power plant to provide energy. The beam is typically either a microwave or a laser beam, and it is either pulsed or continuous. A continuous beam lends itself to thermal rockets, photonic thrusters and light sails, whereas a pulsed beam lends itself to ablative thrusters and pulse detonation engines. The rule of thumb that is usually quoted is that it takes a megawatt of power beamed to a vehicle per kilogram of payload while it is being accelerated to permit it to reach low Earth orbit. Other than launching to orbit, applications for moving around the world quickly have also been proposed. Background: rockets are momentum machines. They use mass ejected from the rocket to provide momentum to the rocket. Momentum is the product of mass and velocity, so rockets generally attempt to put as much velocity into their working mass as possible, thereby minimizing the amount of working mass that is needed. In order to accelerate the working mass, energy is required. In a conventional rocket, the fuel is chemically combined to provide the energy, and the resulting fuel products, the ash or exhaust, are used as the working mass. There is no particular reason why the same fuel has to be used for both energy and momentum. In the jet engine, for instance, the fuel is used only to produce energy. The working mass is provided from the air that the jet aircraft flies through. In modern jet engines, the amount of air propelled is much greater than the amount of air used for energy. This is not a solution for the rocket, however, as they quickly climb to altitudes where the air is too thin to be useful as a source of working mass. Rockets can, however, carry their working mass and use some other source of energy. The problem is finding an energy source with a power-to-weight ratio that competes with chemical fuels. Small nuclear reactors can compete in this regard, and considerable work on nuclear thermal propulsion was carried out in the 1960s. But environmental concerns and rising costs led to the ending of most of these programs. A further improvement can be made by removing the energy creation from the spacecraft. If the nuclear reactor is left on the ground and its energy transmitted to the spacecraft, the weight of the reactor is removed as well. The issue then is to get the energy into the spacecraft. This is the idea behind beamed power. With beamed propulsion, one can leave the power source stationary on the ground, indirectly heat propellant on the spacecraft with a maser or a laser beam from a fixed installation. This permits the spacecraft to leave its power source at home, saving significant amounts of mass, greatly improving performance. Laser propulsion. Since a laser can heat propellant to extremely high temperatures, this potentially greatly improves the efficiency of a rocket, as exhaust velocity is proportional to the square root of the temperature. Normal chemical rockets have an exhaust speed limited by the fixed amount of energy in the propellants. But beamed propulsion systems have no particular theoretical limit. Microwave propulsion. In microwave thermal propulsion, an external microwave beam is used to heat a refractory heat exchanger to greater than 1500 K, in turn heating a propellant such as hydrogen, methane or ammonia. This improves the specific impulse and thrust-weight ratio of the propulsion system relative to conventional rocket propulsion. For example, hydrogen can provide a specific impulse of 700 to 900 seconds and a thrust-weight ratio of 50 to 150. A variation, developed by brothers James Benford and Gregory Benford, is to use thermal desorption of propellant trapped in the material of a very large microwave sail. This produces a very high acceleration compared to microwave pushed sails alone. Electric propulsion. Some proposed spacecraft propulsion mechanisms use power in the form of electricity. Usually these schemes assume either solar panels or an onboard reactor. However, both power sources are heavy. Beamed propulsion in the form of laser can be used to send power to a photovoltaic panel for laser electric propulsion. In this system, Careful design of the panels is necessary as the extra power tends to cause a fall-off of the conversion efficiency due to heating effects. A microwave beam could be used to send power to a rectenna for microwave electric propulsion. Microwave broadcast power has been practically demonstrated several times. Rectennas are potentially lightweight and can handle high power at high conversion efficiency. However, rectennas tend to need to be very large for a significant amount of power to be captured. Direct impulse. A beam could also be used to provide impulse by directly pushing on the sail. One example of this would be using a solar sail to reflect a laser beam. This concept, called a laser-pushed light sail, was analyzed by physicist Robert L. Forward in 1989 as a method of interstellar travel that would avoid extremely high mass ratios by not carrying fuel. His work elaborated on a proposal initially made by Marx. Further analysis of the concept was done by Landis, Malov and Matloff, Andrews and others. In a later paper, Forward proposed pushing a sail with a microwave beam. This has the advantage that the sail need not be a continuous surface. Forward tagged his proposal for an ultralight sail, StarWasp. A later analysis by Landis suggested that the StarWasp concept as originally proposed by Forward would not work, but variations on the proposal continue to be proposed. The beam has to have a large diameter so that only a small portion of the beam misses the sail due to diffraction, and the laser or microwave antenna has to have a good pointing stability so that the craft can tilt its sails fast enough to follow the center of the beam. This gets more important when going from interplanetary travel to interstellar travel, and when going from a flyby mission to a landing mission to a return mission. The laser or the microwave sender would probably be a large phased array of small devices, which get their energy directly from solar radiation. The size of the array obsoletes any lens or mirror. Another beam-pushed concept would be to use a magnetic sail or MMPP sail to divert a beam of charged particles from a particle accelerator or plasma jet. Jordan Carr has proposed a variant to this whereby beam of small laser-accelerated light sails would transfer momentum to a mag-sail vehicle. Another beam-pushed concept uses ordinary matter and works in vacuum. The matter from a stationary mass driver is reflected by the spacecraft, cf. mass driver. The spacecraft neither needs energy nor reaction mass for propulsion of its own. Proposed systems. Lightcraft. A Lightcraft is a vehicle currently under development that uses an external pulsed source of laser or maser energy to provide power for producing thrust. The laser shines on a parabolic reflector on the underside of the vehicle that concentrates the light to produce a region of extremely high temperature. The air in this region is heated and expands violently, producing thrust with each pulse of laser light. In space, a Lightcraft would need to provide this gas itself from onboard tanks or from an ablative solid. By leaving the vehicle's power source on the ground and by using ambient atmosphere as reaction mass for much of its ascent, a Lightcraft would be capable of delivering a very large percentage of its launch mass to orbit. It could also potentially be very cheap to manufacture. Testing early in the morning of the 2nd of October 2000 at the High Energy Laser Systems Test Facility, Lightcraft Technologies, Inc., with the help of Franklin B. Meade of the U.S. Air Force Research Laboratory and Light Mirabo set a new world's altitude record of 233 feet for its 4.8-inch diameter, 1.8-OUNCE, laser-boosted rocket in a flight lasting 12.7 seconds. Although much of the 8:35 a.m. flight was spent hovering at 230-plus feet, the Lightcraft earned a world record for the longest ever laser-powered free flight and the greatest air time from a light-propelled object. This is comparable to Robert Goddard's first test flight of his rocket design. Increasing the laser power to 100 kilowatts will enable flights up to a 30-kilometer altitude. Their goal is to accelerate a 1 kilogram microsatellite into low Earth orbit using a custom-built, 1 megawatt ground-based laser. Myribo's Lightcraft design is a reflective funnel-shaped craft that channels heat from the laser towards the center, using a reflective parabolic surface causing the laser to literally explode the air underneath it, generating lift. Reflective surfaces in the craft focus the beam into a ring, where it heats air to a temperature nearly 5 times hotter than the surface of the Sun, causing the air to expand explosively for thrust. Laser thermal rocket. In 1992, Jordan Carr proposed a simpler, nearer-term concept which has a rocket containing liquid hydrogen. The propellant is heated in a heat exchanger that the laser beam shines on before leaving the vehicle via a conventional nozzle. This concept can use continuous beam lasers, and the semiconductor lasers are now cost-effective for this application. Microwave thermal rocket. In 2002, Kevin L.G. Parkin proposed a similar system using microwaves. In May 2012, the DARPA, NASA Millimeter Wave Thermal Launch System project began the first steps toward implementing this idea. The MTLS project was the first to demonstrate a millimeter wave absorbent refractory heat exchanger, subsequently integrating it into the propulsion system of a small rocket to produce the first millimeter wave thermal rocket. Simultaneously, it developed the first high-power cooperative target millimeter wave beam director and used it to attempt the first millimeter wave thermal rocket launch. Several launches were attempted, but problems with the beam director could not be resolved before funding ran out in March 2014. Non-spacecraft applications. In 1964, William C. Brown demonstrated a miniature helicopter equipped with a combination antenna and rectifier device called a rectenna. The rectenna converted microwave power into electricity, allowing the helicopter to fly. In 2002, a Japanese group propelled a tiny aluminium airplane by using a laser to vaporize a water droplet clinging to it. And in 2003, NASA researchers flew an 11-ounce model airplane with a propeller powered with solar panels illuminated by a laser. It is possible that such beam-powered propulsion could be useful for long-duration, high-altitude, unmanned aircraft or balloons, perhaps designed to serve, like satellites do today, as communication relays, science platforms, or surveillance platforms. A laser broom has been proposed to sweep space debris from Earth orbit. This is another proposed use of beam-powered propulsion, used on objects that were not designed to be propelled by it. For example, small pieces of scrap knocked off satellites. The technique works since the laser power ablates one side of the object, giving an impulse that changes the eccentricity of the object's orbit. The orbit would then intersect the atmosphere and burn up.